So we looked at the small signal parameters, small signal values, transconductance, RO and R pi for BJTs. Let's see how they're going to do us some good. So those values all tell you about changes. They're all derivatives. And what the amplifier that you've been building looks something like this. You've got your amplifier, and then you have a DC value that you put on the base to get your current. So you want to have a default current through your amplifier. So when there's no moving signal on your input, you just get that constant current going through your amplifier. So that's this DC voltage here, and that comes from your current mirror now. Your current mirror provides this voltage. And then we saw that there was an AC coupling capacitor that takes V in. The way it's drawn in on this picture is, instead of using the AC coupling capacitor, I wrote a little V in here with a little wavy thing to show it's just a little moving signal there. And so essentially what's happening here is your current mirror, that the current mirror is putting a default voltage on your base, and then your V in, the moving part of your V in signal, is being added to that voltage. So what's happening here is, if you have a sine wave on the function generator, it goes around 0. So it would go above 0 and below 0, above 0, below 0. When you set an offset, it moves that sine wave up to whatever value you set as your offset. In this case, this is acting like an offset. And then the AC coupling capacitor, if you remember, AC coupling capacitor, if you have a sine wave over here, the DC part of it disappears and just the moving part of it shows up on the other side. And whatever voltage was kind of the default voltage on this side, that will end up, it will offset this moving part of the signal here to whatever voltage you have set on this node. So hopefully that makes, that works. And again, just reminding you of the shorthand, lowercase vn, that's shorthand for delta vn. And when I write in capital letters, that is the DC voltage. So that's why this is in capitals, and that's in lowercase. And when you have a signal that has both moving and DC parts of it, you have a capital first letter and a lowercase subscript. Okay. So lowercase is just the moving signal, all uppercase is just a DC value, and a capital first letter and then lowercase means that it's both added together. And what you're getting at this node right here is these two voltage sources added together. So if I wanted to write the correct name here, this would be V lowercase n. Okay, so now we've got this picture where we've got the moving part of the signal separated from the DC part of the signal, the biasing part of the signal. And let's go one more step here. And I actually tried to do this video, but I didn't like where things were going. The total story of this circuit is the DC part, which sets your current, and then the moving part, which turns that current up and down and makes V out move. So there's actually two parts to this circuit. And when you're talking about small signal analysis and small signal model and all that, what you're doing is you're separating those into two stories. The DC biasing, which you did in lab and on the homework for this week, that sets a DC current through your amplifier, and it's a DC voltage on the base. And this is the DC part of the circuit. And then on top of that, you have your moving signal, which has your moving V in and your moving V out. And it turns out this model right here, since your second circuit here is only interested in the moving part of your signal, this model right here isn't appropriate for that. It takes voltages in and puts current through them, but not changes in voltages and changes in current. So the small signal model is what you replace this transistor with, that only deals with changes in things. Okay, and that's one part of the story, that you need something to replace this, because this deals in voltages and currents, but you need something that deals in changes in voltages and changes in currents. So you need to replace that. But the other part of the story is that since your total circuit story is this thing up here, the sum of these two parts, the moving part and the DC part, it turns out that you can use a trick that you probably learned in Circuits 1. And it turns out that if you're in a legal small signal region, in other words, this V in right here is small enough, even on, let's look at the VBE versus the IC. If you look at this whole thing, that's curved. But if you looked at just a little piece of it, like from here to here, that pretty much looks like a line. So that says when you change VBE, the current changes linearly with that. It's not true. This is a curved line. But if you look at a small enough section of it, you can treat it as a line and be pretty close to right. It's another approximation to make calculations easier. If you take the whole thing, that's curved, and you're going to get very different values if you look here and here. You can tell the slope's completely different. But okay, so for a legal small signal region, you're taking a piece of the graph that's small enough so it pretty much looks like a line. So you can treat it as a line. And that means that if you're in a legal small signal region, in other words, Vn is moving a small enough amount, this is a linear equation. It becomes a linear circuit. And with a linear circuit, you can use superposition. Okay. Superposition, if you remember, you take, zero out all the sources except for the one that you're interested in. Well, actually, you zero out, you keep only one of, let's say you had 5 sources, that here you have less, but let's say you had 5 sources. You'd zero out 4 of them and solve the problem for the one that you kept. And then you'd zero out 4, a different combination of 4, and you just have one source. I should draw it. But hopefully you remember what superposition is. So I'll stop trying to explain it in the air. But it turns out that if you keep your circuit operating in a small enough region where you can treat this linearly, you can take this DC part of your circuit and treat it as one problem. That's your current mirror and your biasing you did on the homework. And then you can take this other part and treat it separately. Okay. And then if you wanted to get the whole story, you'd add them together to get the complete description of how the circuit behaves. Okay. If you look at your original circuit, let's chop this off. If you look at your original circuit, if you're doing superposition, then you zero out you zero out all but one source. Now, if you look at the DC part of the circuit, having this DC source here and this DC source here, you kind of need that to figure out your current. But that's a separate problem, and that works well there. But then when you go to the moving part of the circuit, you only want to keep the moving input of the circuit. This up here, that's a DC source. That's a DC source. So in superposition, what you would do is you would say, okay, this is, I took care of this when I did the biasing part of the circuit. So remember, the circuit's in two pieces. This source right here gets taken care of when you do the biasing part of the circuit. And then you say, well, this also up here, this is a DC source. So I am going to zero that too, make that grounded. Now, if you look at this, this makes absolutely no sense. If you ground that node up top, then this circuit will not work. And so again, that's another reason we need a new model for the transistor. This just does not work. We need something here that will work when you're doing superposition, when you're just doing this one piece of the moving input and watching the moving output. We need a new model for that. But back to the point of this video, the main point of this video is that when you're doing small signal analysis, what you're doing is you're just looking at the moving part of the circuit. And when you're doing small signal analysis in legal small signal region, then this behaves like a linear circuit, and you can use superposition, which means once you figure out the DC part of it, you can zero them, and you end up with a circuit that looks like this. The supply will be grounded, ground will be grounded, any DC offset on the input will be grounded. That goes away. And you end up with something like this. But again, this model right here isn't appropriate for that. So we need to replace that with something, and that will be in the next video.